Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 22nd, 2025, about 5 days ago. The big result is a full information drafter selector called Spec that evaluates every drafter from a single verified trajectory and delivers up to 83.7% token per second improvement, with provable no regret. The paper is titled Not-a-Bandit, Provably No Regret Drafter Selection and Speculative Decoding for LLMs. And as we'll see later, the implications for inference speed and reliability are quite significant. Beyond speed, it scales logarithmically with drafter count, adds minimal overhead, and stays robust under distribution shift. Alright, the introduction set the stakes with full information selection and no regret guarantees. Figure 1 presents the motivation and the payoff. The left panel shows domain experts that shine in their niche but degrade off domain, which makes fixed routing brittle. The right top workflow illustrates drafting, verification, then a lightweight evaluation that scores every drafter from one verified path. The right bottom bars report speedups, with Spec reaching roughly 5 times across targets. Well, Figure 2 clarifies how the conditional acceptance probability works in the draft tree. The diagram shows that gamma k represents the total chance of accepting any token at a given level, not just the single realized token, which matters for unbiased estimation. The top band visualizes gamma 1 across all first children. The middle band highlights gamma 2 over second-level nodes. The lower box marks gamma 3, and together these levels explain why one verified trajectory suffices without exploring alternative branches. So Figure 2 clarified why one verified path gives full feedback. Table 2 reports the overhead, which isolates 3 costs: a llama forward at about 76 milliseconds, an eagle forward at about 2.5 milliseconds, and the hedge update at about 0.41 milliseconds. The drafter pass is roughly 1/25th of a target pass, so evaluating several drafters barely moves latency. Even a small rise in acceptance therefore pays for itself, because it reduces expensive target calls. So Table 2 broke down overheads. Table 1 reports performance and throughput for 7 domain drafters against Llama 3.18 BIT. The diagonal shows strong in-domain gains, while off-domain efficiency drops, so any single drafter averages worse than the vanilla eagle. Concrete standouts include the CNN-DM drafter on its own domain, and the SQL drafter with the highest accepted length and token per second. The rightmost columns summarize lower averages across domains. Alright, Table 3 compares accepted length and token per second across methods. Spec leads on every target, which matters, because higher acceptance reduces costly target passes. On Llama 3.18 BIT, it reaches MAT, about 7.69, and token per second, about 103, with best averages near 7.15 and 90. On QN38B, it lifts equal to MAT, about 7.52 and 82 tokens per second, topping averages at 6.37 and 69. For QN332B, gains are smaller yet consistent, averaging about 6.21 and 40. So Table 3 showed throughput gains across targets. Figure 5 presents 2 views of why that happens. The left panel plots cumulative regret over normalized steps, where Spec stays almost flat at 0, while the bandit baselines climb steadily because they only get partial feedback. The right panel shows MAT as the number of drafters grows. Spec remains near the best drafter line, above the eagle baseline, while bandit methods degrade sharply. Alright, 2 takeaways stand out. Full information drafter selection from one verified trajectory delivers provable no regret and sizable throughput gains, and the approach scales logarithmically with more drafters while staying robust under distribution shift. The implication is faster, cheaper, and steadier large language model inference across domains. Thanks for listening. I am Alex, signing off from AI Research Roundup.